Hello, this is Dr. Adelberg, and our presentation today is mechatronics modeling. We'll follow the textbooks of W. Bolton, 4th edition, and we are in chapter 11 and 12, talking about the mechanical, electrical, hydraulic modeling and dynamic response with simulation. The way that modeling is taking part in the design process is shown over here. We start with our understanding of a need. When we start our design process, system specifications will tell us what is it that the need is quantified to. Then we come up with a conceptual design and develop a mathematical model for the concept. Then we do system analysis and simulation. We optimize the analysis, and then we start the design with the optimum parameters. The different modeling that we need to consider when we design electromechanical system are precision, kinematic, dynamic strength, thermal, fluid flow, electrical, and control. The modeling is based on a sketch which shows the different variables and parameters, as well as the mathematical relationship between the variables and the parameters. Here we have a mass spring damper system with a variable that is the positioning of the mass. We have also a function, a forcing function, which drives the mass, and we have system parameters, which are the mass, the damping coefficient, and the stiffness coefficient. And that is the equation of motion that mass times acceleration equals to the spring force and the damping force. We bring them into the other side, and we equate that to the forcing function. So that is the summation of forces equal to 0, and the forcing function is equal to all the resisting forces, which is inertia, damping, and stiffness. In 2 degrees of freedom, the equations become a little more complicated. We see here the summation of forces on the first mass, summation of forces on the second mass. We see over here also the different parameters, the free body diagram, and the equations of motions in a matrix format. This will require a analysis tool like MATLAB, as well as various eigenvalue analysis that will let us know what are the various natural frequencies, and also with the forcing function, what would be the dynamic response. Here's an example of a dynamic model in rotational mechanism. We have here 2 robot links, and the equation of the equilibrium equations on the first link is equal to the various forces that act at the joints, including the inertial force, which is minus the mass times the acceleration of the first link. And then we have the summation of moments of the first link, which equal to the moment at the joints, which are applied by the frame or by the adjacent joint or by a gripper or by a work. And then this is equal to the, we sum all the moments about the center of gravity that has to be equal to 0, and including the inertial force, which is actually here an inertial moment. And we have the same thing for the link 2. And then again, when we break this down to the different vector equations, it becomes matrix equations, which we could solve it using vector algebra with MathCAD or MATLAB. Here's an example of modeling of a robot link in 3 dimensions. This is a bit more complex, but the principles are the same. Summation of all forces on this free body diagram must equal to 0. We have the forces on the one joint, and we have the forces on the adjacent joint. We have the inertial force, which is minus mass times the derivative of velocity, which is vector. A derivative of velocity is acceleration, mass times acceleration, plus we have the gravitational force. So this is the vector equation of summation of forces equal to 0. And then we have the rotational equation, the summation of moments. So we have a moment that the previous link is acting on this link at this joint, which is n with this subscript. And we have similarly an n, which is the torque, which the next link is acting on this link, and that is designated over here. And then we have the, this is the two torques at the joints, and then each force that we found earlier in the force equation has a moment about the center of gravity, which is the radius vector from the center of gravity cross the force itself. And we have two forces, so we have to add these two. And then we have the inertial torque, which is I times alpha, or omega dot is alpha, the angular acceleration of this link in 3-dimensional. And then we have on top of it the gyroscopic effect, which is the cross product of the moment of inertia times the angular velocity of this link crossed with the angular velocity. And the moment of inertia is a complex form in 3 dimensions. This is the principal axis, and these are the cross axis inertias. When we do it in a simpler formulation, such as this particular mechanism, we could write equations of motions pretty much mathematically, come up with the final vector equation that says that the total acceleration at the tip of this mechanism equal to the acceleration of the base, whatever this base is, if it's perhaps moving, times the centrifugal acceleration, which is omega cos r, plus the tangential acceleration, which is alpha angular acceleration cos the radius vector, plus the Coriolis, which is 2 omega cos the linear velocity, relative velocity, plus the relative acceleration of this point with respect to the rotating system. So that could also be solved in using graphical solution. We see here an example with numerical values and a graphical solution over here. We also have to deal with precision and accuracy of mechatronic systems, and the definitions of the basic variables are the accuracy of a variable is how far it is centered around the target point. The precision is how far all the points are close to each other, as we see over here. And being accurate and precise is shown over here as hitting the bullseye with the variables being very close to each other. It's important to realize that the variables are statistical. Almost all the variables are statistical. And when we talk about statistical variables, we typically have two parameters that define them. One is the mean, the average value, and the other one is the standard deviation, how dispersed is the distribution of all the points around the mean. We see here an example of a robot which is programmed to move to a certain target position, which is right here. And the points over here show where the position is actually happening. And then this position has an average. And then the definition of average accuracy is the difference between the average position and the target position. And then the distribution of all these points about the average position, which is determined over here by sigma. It's the square root of the sum of each one of these points, the difference between it and the average position squared, divided by the number of samples, -1. This is the standard deviation. And the mean, or the average, is the sum of all these points divided by the number of points. Then we do this in a linear continuous form and not just in point-to-point. Then what we see is that we get a curve. If we move in one direction, and a different curve when we move in another direction. And we do this several times, and we measure it precisely with a laser interferometer. Then we could determine the average accuracy, which is now this dashed line as a function of the position. And then we have the repeatability, which is the largest gap between the two extreme curves. And we have the total accuracy, which the maximum distance between the maximum point and the minimum point. So this is the accuracy. We could linearize non-linear functions such as this by taking the maximum error divided by the minimum error, and then this error divided by the total travel will give us the slope of this linear line, which we can use then in a controller to calibrate the position and remove the deterministic error. We cannot remove, however, the statistical error, which is the repeatability. Over here, we see an example of a general kinematic diagram of a robot where all the links and joints are expressed over here in a vector formulation. So the linear displacement at each and every joint is described here by a vector, dq, and the linear displacement at the end of the mechanism is described by another vector, which is p. And we can relate the deviation of position in p as a function of the deviation in q. This is pretty simple mathematical expression. And in order to find the accuracy at the point, for example, of a gripper of that robot as a function of the accuracies of each one of these links, then what we do is we take the Jacobian of the relationship between the output position and the input position, the position of the gripper and position of the joints. And then what we get is that the delta of the U positions, all these small displacement at the gripper equals to the Jacobian times all the small displacements at the joints. Now we can find the Jacobian by taking the forward kinematics based on a simple kinematic diagram. We could do the transformation of a coordinate system from a moving coordinate system to a stationary coordinate system, and from one moving coordinate system to the other. It's a simple transformation matrix that has cosine of the angle between the two coordinate systems on the diagonal, and then minus sign and sign on the off diagonal, depending whether we convert in the rotating with respect to the stationary or the stationary with respect to the rotating. Once we go through these derivations, we could solve for the Jacobian matrix and use it in order to construct a precision analysis tool such as this one, where we have a model right in here for a system, and the model allows us with simple Visual Basics or C++ or C#, write or for that matter on Excel spreadsheet, write a relationship between the specifications of each one of these axes and the precision at the point of interest, repeatability or accuracy. And we can also find the effects of each one of these stages on a final result. We can optimize the parameters as we see over here, or even change the stages in order to meet the desired specified target. Here we see an example where we use a simple model, a motion model of a stage. We may have to move this stage for a particular process in a certain profile. And then we may need to determine the motor force, the motor torque, the current, and we use these in order to this kinematic formulation in order to write the dynamic equations and then determine the required forces. One way that it's done nicely with nice graphical representation of the solution is so-called numerical analysis. We take the differential equation and we pretty much define the variable such as acceleration as the integral of the jerk times delta t. So if we sum up all the jerks that we had at a certain given point on Excel spreadsheet and multiply it times a very small increment of time, then we get the next corresponding acceleration. And we can do the same thing for velocity and displacement, and the results are very nice. Doesn't take very long to develop it. We may do some exercises later on in the lab assignments. When we're talking about force analysis, again, we take the free body diagram. We have to account for all the forces, the inertial forces, gravitational forces, friction forces, process forces, add them all up, sum them to zero. And the inertial forces may be dynamic. A steady state is just mass times acceleration. And if it's dynamic, it's mass times dv dt. And then we have to integrate that. Over here, we see an example of a mechanism, a robot, which lifts a car. And we're interested to know what is the deflection, the stiffness. Very important parameter of a system is the stiffness. It affects the natural frequency, which in turn affects the bandwidth of the servo system, as we'll see later. So in this particular formulation, we find that when we go through the derivation, that the change in position is basically related vectorially to the change in the force. Position could be linear as well as rotational, and there is the compliance matrix G, and the compliance matrix is equal to the Jacobian times the inverse of the stiffness matrix times the Jacobian inverse of the Jacobian. So we could also define the stiffness for each joint experimentally, and then add them all up in a matrix to get the total stiffness matrix. We invert it in MATLAB, MATCAD, and then do the multiplication, matrix multiplication, and we can calculate what is the deflection of that robot, knowing the stiffness of each one of this joint which we measures, or if this robot is pressing against a work, we can also find what is the force which we apply just by measuring the displacement. That can later be used in machine learning program which could control the variables of the servo system of the robot. Here we see another example of a second order system for the resistor, capacitor, and inductor, all in a series. They're very analogous to the mass spring damper system. We see here that the solution of the system is also very similar with the electrical. We have two parameters. One is the natural frequency, which is the square root of one of the inductance times the capacitance. Henry and Farad will give us in radians per second. And then in natural frequency of the mass spring damper system is the square root of K over M, stiffness divided by mass. Stiffness is Newton per meter and mass is kilogram. And also we have the relationship between the damping of the system, where the relationship is 2 times the damping zeta times natural frequency as we found over here is equal L over C, and over here equal B over M. And the damping coefficient basically determine how much overshoot we have in the system. So when we design a mechatronic system, and we like to assure that we are not overshooting too much, then we'll have to pick up an optimum set of parameters, such as the inductance and the capacitance, or the damping and the mass and a spring, to provide us the desired results. Here we see a more complicated system, which is a fluid system. And we see here the Navier-Stokes equation. And the Navier-Stokes equation in 3D include the continuity equation, equilibrium equation, momentum equation. And then you see over here the variables. You see that the derivative of velocity, okay, which is acceleration, time rho, which is the mass, and all equal to the pressure gradient, which is the force, and then also the gravitational force, as we saw earlier. And then there are also elements of diffusion, if we have sources within the system. And also over here we have, this is the total derivative, so the differentiating by part, we get this form. So when we add it all up, we could design a sizing tool for a system that does an analysis, simulation of an electromechanical system. What we see here is a system that includes a controller with a set of parameters PID, a stage with a set of parameters of mass spring and damper system. They all work with a closed loop with a feedback from an encoder sensor. And then we set up the parameters here automatically. With these parameters, we can get the stage characteristics, including natural frequency, over here it's in hertz, and damping coefficient. And then we could also see, as we'll talk on the next lecture, the frequency response of this a particular system. We can use it to optimize the parameters and obtain settling time and response behavior as expected in a specification. This completes our presentation, and we continue with more on frequency response in upcoming lectures. Thank you.